Today, I'm going to show you how to use GenomeEditor 2.0 to design a CRISPR project. The example we use is a knock out a human EGF gene and knock in a cassette, which is CMV EGFP iris pure cassette. The process of the design are outlined here, generally divided into two sections. One is data preparation. Second is the design of CRISPR project. In the designing CRISPR project, we need to design a guide RNA, need two oligos with adapted sequence for cloning. We also need to design a donor vector. Here is two homologous arm flanked with a pre-designed cassette, which is CMV EGFP iris pure cassette. After we design the donor vector, we need to design a PCR primer for verify the knockout and the knock-in. To use the program, actually is pretty easy. First, you need to double-click on the program icon to launch the program. In this program, we enter either accession number of EGFR or sequence of the EGFR in this box. So let's use accession number of the EGFR, which is NM_00522A. After enter the accession number, just click on the Submit button, and this will download EGFR sequence information from NCBI. Once the information comes back, we just click on the Process Data button, and this will record the sequence information to the program. Once this is completed, click on the BLAST genome database. And now we'll navigate to the Genome BLAST entry page. Enter the accession number into the box by right-click on the mouse and select Paste. And then submit BLAST project to NCBI. Wait for the BLAST data to come back. This depends on the traffic to the NCBI. Now the data is come back. Click on the process data. So all the BLAST information was recorded in this table. And then you click on the step 1, select exon group. So all the potential exons will be joined on this picture box, and each exon was aligned to the transcript. And then we click on the step 2, verify the exon. This will verify whether the exon is real or not, and then make an entire gene structure. So we click on the step 2. So this entire EGFR gene structure was drawn, and all the information was stored in the program. This completes the data preparation process. So next step is to design a CRISPR project. We click on the Export Genome Editing Design. So the genome design form will show. On the top panel of the form, you can see all the amino acid residue location on the contig was mapped. Entire 1,211 amino acid residue was mapped to the contig. Also, each of the exon location also mapped and stored in this joint drop-down menu. To design a knockin, knockout project, first we need to select the focal point. We are going to delete a portion of the gene, start from ATG, and the deleted region is 200 base pair, and you can change by typing the desired deletion region. And then you can select the length of the homologous arm. The default is 700. So once this is set, just click on the download the sequence button. And when the sequence coming back and will record, list in this sequence box, and then the sequence will translate into amino acid residue. As you can see, the first amino acid residue is methionine. This indicates the downloader is correct and it's precise. And the other portion of the genomic sequence was also downloaded and stored in the program, including 5' arm, 3' arm, and select the region, and also other useful plus minus 50, 75 of the sequence surrounding the ATG. So the first step of the designing CRISPR project is to design a guide RNA. So we will select guide RNA from these 200 base pairs. So we export the sequence to a guide RNA select form. In this form, all the potential of a guide RNA with a varied PAM sequence is stored in this table. Currently, this program doesn't have the ability to do the off-target evaluation. What we can do is we copy a sequence, a region of sequence you want to design of the guide RNA, and browse genome, and to see if they have other match, non-specific match. If there's a specific, then you can select the sequence. Once you decide the guide RNA sequence, you just click on the sequence, and the sequence will show in this sequence box. And next, once you select the guide RNA sequence, and you select your vector system, we'll use Zhang Feng's lab's vector system, say 459. And design the 2 oligos for cloning. Will automatically design the 2 oligos for generate this guide RNA, and then it will automatically adopt the sequence fit into that vector. So you can copy the oligo sequence and for order. And this complete the design of the 2 oligos for a guide RNA. So once you design the guide RNA, the next step is to design a donor vector. To design a donor vector, the first step is to check the box for the assembly. So the first piece of guide RNA is the 5' homologous arm. So this picture will show in here, and the sequence will in this sequence region. So next, we'll select the cassette, pre-designed cassette. We said we're going to use the CMV, EGFR, EGFP, IRAS Pure. So you select the pre-designed cassette. You can input your cassette into the program. So then we add the 3' arm into the donor vector. So this will complete of the design of a donor vector. Once you finish the design of the donor vector, the next thing is to design PCR primer to verify the knock-in, knock-out after the experiment. To design the primers, it's very easy. You just click on the Export Primer Design. And then the design form will show. On the top panel of the design form, this line indicates the entire sequence. And these two vertical lines indicate the junction of a 5' arm. Upstream of the 5' arm is a 5' flanking region in the genome. And downstream of the 5' arm is the cassette sequence. To design a PCR primer to verify the knock-in, knock-out, you need a design primer in the 5' flanking region and the cassette region, so then your PCR is going to be unique if your knockout, knock-in is successful. And to do that, you just click on the 5' integration detection. So these 4 guidelines define the region to pick a primer will automatically set in the location for design the 5' integration. Just click on the design. So 2 pairs of PCR primer will be designed. And this can be used for the nested PCR. And if the 1 pair primer is not successful. To design a PCR primer to detect the 3' integration, you just click on the 3' integrations. And this all guideline will move to this region. And the downstream 3' of the homologous arm is the 3' flanking in the genome. So you need a primer in this 3' flanking region and the cassette region. So after you set that, you just design, click on the design, the 2 pair primer will be picked. So by this way, we design the PCR primers to verify the knockout, knock-in of the cassette. So this completed the entire process.